Received her PhD from Cambridge in 2010, was a Hubble Fellow in Hawaii, and after some other postdoctoral work, started at UT Austin in 2015, where she was for 10 years, and she just recently moved to UCSB. She's an expert on formation of dust in early galaxies, late-time universe, as well as the energy distribution of light emission from galaxies both at high and low redshift, and especially as it pertains to infrared emission. And now there's this exquisite new space-based observatory, the James Webb Space Telescope, on which she is leading several surveys, and she will tell us how that revolutionized the field of galaxy formation.
Great starting this.
Thank you.
And we are not recording this, so you can ask dumb questions.
Oh, please do ask some questions. So, just a quick show of hands, who's not an astrophysicist? Okay, great, good. Okay, cool. So my goal is for you to understand this talk, so interrupt me, please. I've lived my entire academic career in astronomy departments, and I'm new to a physics department, so I can appreciate how not all talks are totally accessible to everyone. So please interrupt. I'm really excited to share with you some of the recent results from the James Webb Space Telescope. This has been a huge transformation in the field of astrophysics over the past few years. I work on galaxies in the distant universe. I'm an observer. And we found some really amazing things. So I'm excited to share that with you. I want to first give a shout out to many of the members of my group. The folks in yellow are still in my group, but a lot of the work, of everyone from past generations has gone into our ability to do really interesting things. So I just, have really appreciated. You'll see some of the work, but not all. Okay, so if you have read the headlines vaguely inside, well, if you pay too much attention to the news, that might be hard, but these days. But a couple years ago, when JWST launched, so the community first got access to its data mid-2022, it launched December 2021, it was a flurry of really exciting results. Some headlines like this: JWST's first glimpses of early galaxies could break cosmology. Astronomers spotted something perplexing near the beginning of time. And then my personal favorite hyperbolic headline was: the story of our universe may be starting to unravel. So I don't think it's actually quite unraveling, but there is a reason behind all of these headlines, because JWST has indeed surprised us quite a bit. And the gist of the message is that there's too much too early. We have found much more than we expected before JWST launched, and we are finding it earlier in cosmic time, closer to the Big Bang than previously expected. Today, I'm going to share with you results in two ways that we are finding things that are too much too early. The first is through the detection of galaxies, and the most distant galaxies that we can find. And then the second is in supermassive black holes. And many of you have perhaps heard the term little red dots. Little red dots have been recurrent on even All Things Considered a few times. So that's been a big discovery of JWST as well. I'll dig into the details. Now, if you look at these two images, I kind of chose them because it's funny. They just look like little smudges. They both look like little smudges, not like the canonical pictures of galaxies and black holes that you might have mental images of. But the gist of this is we're looking at the early universe. Everything is primordial. Everything is a nugget of what it becomes at much later cosmic times. So keep that in mind. Okay, so for the non-astro folks in the room, I wanted to step back a step further and show you a cosmological model of what we think the universe looks like on very large scales, governed by lambda CDM, or lambda speaking to dark energy, and CDM is cold dark matter. If you insert these rules of cosmology into a cosmological simulation. The distribution of matter evolves with time, collapsing in filamentary structures and collecting at the nodes into galaxies' halos, where, so each galaxy has a dark matter halo, where, collecting all of accreting material with time. And the proportion of matter in that dark matter halo is something like 84% dark matter and 16% baryons. Now, astronomers call normal matter baryons. It's just the heavy stuff. So, it's always funny when physicists I was like, what are you talking about? Yeah, baryons. Okay, so normal matter, and all of the astrophysics, a lot of it is buried in the details of those baryons. I want to show you this plot. This is a star formation history of the universe with cosmic time. Redshift is a nonlinear relationship, has a nonlinear relationship with cosmic time. We have the Big Bang on the far right here, not at redshift 7, at redshift infinity, but time marches towards the left on the top. You see the time after the Big Bang on the top, so it ends at 2 gig years. The universe is 13.8 billion years old, so I'm not showing you a lot of cosmic time here. The y-axis is the stars formed per year, per unit volume of the universe. So this is the star formation rate density. It's the log of that. So long story short, the measurements, the points show you that with time, stars form more and more as halos accrete more stuff, right? So stars become more and more efficient per unit volume. And this is after, divorcing it from cosmic expansion too. This is, per co-moving volume. Okay, so there was a certain expectation from decades of work with Hubble Space Telescope. So this is, this farthest point here is, the farthest that Hubble was able to see around a redshift of 10, which is around 500 million years after the Big Bang. And galaxies, star formation was very rare at those times. There is somewhat of this expectation. I'm going to show you this orange line here. This matches well to predictions from Lambda CDM because you also can model the growth of massive halos with time. And you expect it to have as halos accrete dark matter and baryons, that happens at a certain rate. And if star formation tracks with that rate, then you get the orange line, basically. So, the measurements agree with that orange line. Okay, so enter JWST. We have, so halo growth goes something like that. That's just kind of showing proportional. Enter JWST, we have these blue points now. So you see a deviation from this expectation of halo growth at even earlier times where there's more star formation than expected. And it kind of works out, depends on, you can split hairs the way you describe this, but the abundance of redshift greater than 10 galaxies in the first 500 million years, is something like 10 times higher than pre-JWST expectation. That's kind of the take-home point number one. So the big question here, these two, the set of observations versus our understanding of how halos grow mass with time, is do stars live in dark matter halos? So here you have the stars, here you have the dark matter. Do they grow in lockstep with their halos? In other words, is the halo mass accretion rate or is the star formation rate, the change of the stellar mass, proportional to the halo mass accretion rate? We also just call the change of the stellar mass with time the star formation rate because you're just adding stars. But anyone who works on astrophysics knows that this is a much more complicated picture. Stars are not the only baryon, it's not the only normal matter that exists in galaxies. We also have gas, we also have dust, we also have things like black holes and don't really fit in any other bin. Gas is what's needed to fuel star formation. So that's what we had. Primordial gas is just hydrogen. It passes through various phases before it forms stars, most importantly through molecular hydrogen, before it collapses and forms stars. And then after stars are present, and a byproduct of star formation is the formation of black holes. We understand this, through the death of high mass stars. You get black holes. Those can grow, merge, do other things. And then you also get the production of dust as a byproduct of star formation, usually in the upper atmospheres of evolved stars or through supernovae. And dust is also an important catalyst for forming more stars. So dust intermixes with gas, makes star formation more efficient. So the efficiency of star formation is really in question here because, again, there are really bright galaxies at early times. Stars exist in them, and the halo mass function says that they really shouldn't. There are all sorts of definitions of star formation efficiency out there in the literature. You can characterize this as a stellar baryon fraction. What fraction of baryons live in stars? You can do it as a differential quantity, like the star formation rate over the halo mass accretion rate. But folks who work on the nitty-gritty aspects of star formation, like in the Milky Way and in star-forming regions, would maybe characterize it a bit differently. Whereas the star formation rate, how much gas is consumed in a star formation episode, like you have a molecular gas cloud, how much of that is converted into stars? At maximum, that's around 10%, but it's often much lower, around 2%. And if you look at like free fall times of a molecular gas cloud. So that's just to give you a little context of the discussion of efficient star formation. I want to pivot a little bit and show you this animation of the halo mass function. This is the expectation from lambda CDM, how many halos you have per unit volume above a given halo mass. So this is like how many collections of dark matter halos that are virially bound above a certain mass. So this starts at redshift of 20, which is really primordial times. We haven't seen redshift 20 yet observationally. And it evolves forward to redshift 8. So this is cosmic time after the Big Bang. So I denote 3 halo masses here, 10 to the 8, 10 to the 9, 10 to the 10. These are kind of the typical halo masses of galaxies that we are able to observe for the total dark matter halo. And you can see how it changes. Everything grows with time, so halos accrete matter. But what I want to point out here is that they're growing at different rates. The halo mass function is extremely steep at the bright end. So you see the most growth at the bright end, the massive end, 10 to the 10 solar masses. So if you look on the right plot here, the halo mass density of 10 to the 8 solar mass halos grows by something like 3 orders of magnitude over this epoch, whereas the more massive sources, those grow by something like 7 orders of magnitude over this early epoch. So if we want to test how astrophysics builds galaxies in lambda CDM, it can be very useful to look at the most massive structures, the most massive galaxies at very early times, because there's this just very, very steep drop-off in the halo mass function. So individual massive galaxies serve as crucial testbeds for astrophysical processes within lambda CDM. Okay, so we want to look for the most massive halos. Massive galaxies are expected to be brighter than lower mass galaxies. Maybe that makes intuitive sense. But because you can also see that the abundance, though, is much lower. So they're rarer. They're not as common as lower mass galaxies. So to find them, you can't go to the deepest JWST data set, which is like a single image that's a pencil beam on the sky, a very tiny fraction of the sky. You're not going to find rare sources in that one pencil beam. So you have to go to a wider area of the sky to find them. Okay, so have people seen this image before, the Hubble Ultra Deep Field? Okay. Astronomers, I hope you have. But so the Hubble Ultra Deep Field is such a pencil beam survey. It's one of the deepest images we had prior to JWST, but it's sized to give you an understanding. If you haven't heard this analogy before, it's as if you are holding a pencil at arm's length, and it's effectively the size of the head of the pencil or the head of a pin held at arm's length. It's that much sky. Like, that's a very small fraction of 4 pi steradians. But yeah, it gives us really deep insight. This is, how we know about the distant universe, or tiny, tiny little fields on the sky. We're not able to see the distant universe across the whole sky. Okay, so that's a Hubble Ultra Deep Field. So I lead a team called Cosmos, the Cosmic Evolution Survey. This has actually been a survey that has been going for a very long time. Here you can see the Hubble Ultra Deep Field to scale against the Cosmos field. We're purposefully going wide. This is the scale of the moon on the sky with respect to Cosmos. We're purposefully going wide because we want to find rare galaxies that are brighter and more difficult to find in these pencil beam surveys. Here are a bunch of other, surveys that are used to study the distant universe. And we also want to study large-scale structure at high redshifts at very early times, and so you need area to do that. This is stuff that is a bit inaccessible to all sky surveys. Those are much shallower. What Vera Rubin Observatory will do is much shallower than what we're doing. We're at the nexus of very deep field science and large survey science. We're kind of the largest deep field, depends on who you ask, but the Cosmos survey, I won't go into detail here, but it's amassed a great deal of data over the past 20 years or so. It was initially led by Nick Scoville at Caltech and has been passed on generation to generation. Every telescope on the ground and in space has stared at this patch of sky after a great deal of dedication from everyone. And we were very fortunate in the first year of JWST's observations to get the largest JWST survey off the ground as well in the center of the field. So this white box now has our JWST data. So we went, JWST is roughly able to see objects 100 times fainter than the Hubble Space Telescope. So this has really opened up a new window in the first 500 million years of cosmic time that we just didn't have before. So there's the full Cosmos Webb image. The survey, the JWST survey is called Cosmos Webb. We have a lot of papers out already. The data were taken over a year and a half, just finished in May of 2024. It's actually become a big data project, even though JWST isn't really a big data type of project. This mosaic is really enormous. It's stitched together out of 12,000 individual exposures and lots of dedicated work by our program architects to make sure the images and resulting catalogs are really robust. So just to show you, give you a sense of scale. So here, Jades and Sears are some other JWST deep fields. So Cosmos Webb is 3 times larger than not just these surveys, but all other JWST deep fields combined. And we're able to see a tremendous amount of detail. So I'm going to zoom in by a factor of 2 several times, and it just keeps looking the same over and over again. And I'm zooming in here on a special system that was discovered in the field. It's a perfect Einstein ring. It's the highest redshift Einstein ring that's been found and published in these papers. We also have remarkable other gravitational lens systems present. So I'm not going to talk about that, but wanted to show you some pretty images. Okay, so the first topic, which I've already gotten into, is this concept that there are galaxies that are too bright too early on in cosmic time. Now, how we find galaxies at these great distances is just through the imaging. So we take images of the field at multiple wavelengths and multiple filters, and then we search for what are called dropouts. We're looking for a certain spectral break in galaxies, and of course, because these are in the distant universe, they're cosmologically redshifted by quite a bit, and we're looking at which band they are detected and not detected in. So at redshift 12, you expect no flux in these filters shortward of the Lyman break, and you do expect flux longward of the Lyman break. So this is literally, the hunting game is you try to find flux redward of certain filters, and whichever filter the flux drops out of tells you the redshift of these candidates. So in the early days of JWST, we just found a flurry of candidates of really exciting redshifts that, had I given this talk pre-JWST, would be laughable almost to talk about redshift 13, redshift 17. The redshift 17 candidate turned out to not be right, so we did get a spectrum of that source, and it's actually at redshift 4.9. It was very strong emission lines that were masquerading as broadband flux, just masquerading at different wavelengths. But that's the one, pessimistic, case. Largely everything else has been spectroscopically confirmed that has been followed up. For example, here's a redshift 12 galaxy, confirmed at redshift 12.3. And it has both a near spec spectrum, that's one instrument on JWST, and a MIRI spectrum at even longer wavelengths. So we actually detect H alpha, this bomber line tracing ionized gas and star formation out to redshift 12.3, which is remarkable. Really exciting emission line detections. And then other confirmations, we're just routinely confirming these galaxies out to increasingly high redshifts. The landscape of discoveries looks something like this. So the Hubble detection limit can be traced. It's a strong function of redshift. And then these are, silly astronomer units, magnitudes, absolute magnitudes, where you have really, don't worry about the details, but really faint galaxies at the bottom here, really bright galaxies at the top. Hubble could only see bright galaxies, and they could only see out so far because of the wavelength coverage. JWST can see much fainter. Cosmos Webb, we're not the deepest JWST image by far because we're so big. So they're much deeper surveys, but again, they cover a much smaller area. So all of the identified candidates to date kind of really fill out this early universe domain. Those with spectroscopic redshifts beyond a redshift of 10 look like this. This is kind of it. We haven't gathered a ton of spectra in this regime, but enough. They're all published in these papers, but what I particularly want to highlight is that there are some way up here at the top of the plot. They're really bright. They're unusually bright. And until recently, the highest redshift confirmation is, I think, right here. It's more recent, but this was the most distant prior to that, and it's extremely bright. Really, that is what is surprising. So brightness doesn't translate to mass directly, but you can imagine it vaguely translates to mass. So I'm at the stage of life where I have kids and I read them lots of Dr. Seuss books. So I'm ready to get the Sneetch's Star On machine, where we're faced with this challenge where we have an image of a galaxy. We know how much light there is, and we gotta crank that through some magic box and spit out a stellar mass. And that seems possibly trivial, but there's a lot under the hood there. So just to give you a sense of what's under the hood, you have to understand in any given star forming region what the distribution of stars formed by mass is. This is called the initial mass function. So like a lot of low mass stars, some intermediate mass stars, and very few high mass stars. Now you have to understand how they age. High mass stars die quickly. So, these die off. So if you're looking at a slightly older stellar population, you see a lot of these and not a lot of those. Stars have diverse spectra, and so you have to account for those spectra. And then, of course, galaxies don't birth all of their stars at once. There are different star-forming regions going off at different times. And what we see in this image is the amalgamation of all of that. So there's a lot of complication. And then further, stars make dust, and dust really efficiently reddens the spectrum of stars. So what you get out, this light profile, turning it into a physical understanding of the stellar mass, it's really a house of cards, okay? But we're astronomers, we work in order of magnitude, so we're just like happy if it's right within an order of magnitude. Anyway, there's a great review on this if you're interested. Okay, so now I've converted that last plot from luminosity into stellar mass. We've gone through the star-on machine here. And I want to point out the context of the implied stellar masses we have. So here we have like 10 to the 9-ish solar masses established around redshift 12 to 14. That's 300 to 400 million years after the Big Bang. Okay, now let's look at lambda CDM. Let's go back to that halo mass function. What is formally disallowed in lambda CDM would be masses in this little triangle region. That corresponds to the single most massive halo, in the universe projected on the entire sky. And if we were to detect it, and not only the most massive halo, but all of the baryons in that halo, all 16% of it, were converted into stars at that epoch. That's absolutely not realistic because we know star formation is inefficient. If we then consider, instead of the entire sky, if we look over the area roughly sampled by JWST, that limit comes down, and it's kind of close to some of these masses, right? So these masses are getting uncomfortable. They're not in the gray territory here, but they're getting close. And going back to this comment that star formation is actually an inefficient process, we know this. Here's a lovely simulation by Mike Rudich, the Starforge simulation, showing that there's a lot of stuff there that's not stars. That's the point I want to make. That what actually ends up in a star forming region is a small fraction of the total. So if you even assume, the maximum star formation efficiency seen in the local universe, you might get a total integrated stellar baryon fraction of like 10%, and we're seeing something more like 30 to 60% in these systems. So this is that limit traced out by 10%. And we have galaxies, spectroscopically confirmed galaxies in this territory demanding they're more efficient. Because the stellar mass is there, we see it. Yeah.
So this machine you were showing, in which you are converting photo to stellar mass.
Mm-hmm.
So has this assumption been tested nearby universe? Like, is there an independent way
it's calibrated in the nearby universe, and maybe that's the problem.
Okay. So basically, in the nearby universe, do we have independent way to measure the stellar mass?
Yes. Okay. Yeah. I mean, we measure many things through dynamics. And calibrate it that way in the nearby universe. Yeah.
Thanks.
No, that's a great question. Yeah.
In the error bars of this plot, is this just photometric uncertainty, or is this systematic?
No, it's not all systematic uncertainty. It's like it assumes the IMF is fixed. It assumes some. So within canonical astrophysical assumptions, it's accounting for everything, like star formation history, etc., but not like changing the IMF completely. Okay, So do we believe these stellar masses? You might choose to say your choices are yes or no. Okay, so let's explore no. So some might argue like the star formation history. So when you birth your stars and when they die, can change, is one of those knobs in the star-on machine, right? Like it changes your estimate from getting from luminosity to stellar mass. And if we don't really know the star formation history, we just see a dot of light, right? And there's a lot of like nuanced arguments here that, it's like looking at the tail of the elephant trying to estimate how much the elephant weighs. Okay, this is gonna be hard. But one saving grace here is we're looking at the first 400 million years of cosmic time. You don't have much time to have a strong dynamic range of star formation histories. Just to show you, like you have 500 million years. So how you make your stars to come up with this luminosity. There are a couple of histories. Here's a cartoon of like you could form your stars early on, then you get that stellar mass. Later, that stellar mass, and latest of all gives you that stellar mass. You'll get the most conservative mass estimate if you assume the stars just formed really recently, and even that mass is high for lambda CDM. Okay, so now maybe it's not starlight at all. Maybe we're looking at the supermassive black hole accretion. We do see this, and I'm getting into that next. But if that is our answer of, oh well, this isn't super efficient star formation, then we have a different problem yet, because now we have super efficient supermassive black hole creation. Okay, how do we form 1 million solar masses of a black hole in 400 million years after the Big Bang? Another ball of wax, different talk. Another possibility is that we're not looking at stars, we're not looking at a black hole, maybe we're looking at hot gas or nebular continuum. It's possibly seen around exotic, extremely hot, massive stars, which you might expect are overabundant in the early universe. But it's hard to argue that they'll dominate the spectrum in these particularly bright galaxies. Yeah?
What is meant by the word exotic here?
Oh, just like primordial pop 3 stars, really massive stars that are pretty darn rare in the universe today.
Among the theorists, they would be like quark stars would be exotic to them.
Oh, okay, yeah. Good normalization. Okay, thank you. Thank you. Exotic to astrophysicists, not actually
Just
exotic. Just still normal matter. Yeah. Still just hydrogen, but just hydrogen. Yeah, that's right. Okay. Okay, or we could choose to believe the masses. That's the other alternate. And there are theories about how this might happen. So here's another nice simulation out of Starforge that asserts that there are scenarios, rare in the universe today, where simulations indicate that you can produce really efficient star forming regions. So this is a star forming efficiency as a function of the surface density of a giant molecular cloud. And under very dense scenarios with little feedback, you can form a tremendous amount of stars very quickly, and perhaps that dominates at these early times. Maybe not, I don't know. We don't have a ton of data. It's been a couple years, but the process is slow. Not many of these very bright galaxies have a lot of spectra yet. There are 3 galaxies in this luminosity class that have spectra beyond a redshift of 10. Here they are. One was the one discovered by Hubble, which we think is possibly dominated by an AGN. Another that looks to have really high ionization star formation, and another spectrum that is otherwise featureless. It's a spatially extended source. The point is, we gather spectra of these, we learn a lot, but the 3 spectra that we have are all wildly different from one another, so we don't know what dominates the emission here. So one thing we're trying to do in cycle 4, which is happening now, the 4th year of JWST observations, is take more spectra of such extraordinarily bright objects. We have a lot of them in Cosmos because we cover so much area, we can find those rare sources, and this is the Zenith program. So we get our first data in like a couple weeks, and we're really excited about that. I have nothing to show you though, so we're going to move on to supermassive black holes. There are a lot of those too. So this is a really interesting story that actually started out as a massive galaxy problem. So this is a Nature paper that came out. This was submitted to arXiv like 2 weeks after we got the first data, very early onset of massive galaxy formation. And here you see pictures of said galaxies. They found galaxies that had extraordinarily high stellar masses in a regime, redshift regime, that would really test the limits of baryonic processes in lambda CDM. Just to show you measurements of the stellar mass density versus stellar mass, how common these galaxies are. And these galaxies are something like 100 times more common than expected from Hubble, or 10, greater than 10 to the 4, like absurd numbers. This was just still 2 weeks after launch, so it was really exciting. These galaxies were, such universe-breaking galaxies, were identified through the double break technique. It's really kind of a clever technique. So here you see the spectra of some of these sources from the early paper. And the double break refers to first the Lyman break, which I showed you already in this plot. Again, remember the movie, this is how we select the galaxies in the first place. Short word of effectively Lyman alpha, but the Lyman break, you see no emission because that light is absorbed by the intergalactic medium. And so you see a strong spectral feature at the Lyman break. And then the Balmer break, you also see a strong spectral feature if you have an old stellar population. So as a stellar population ages, those really young massive stars die off, leaving A stars, which are still pretty big, but not quite as big. They dominate the spectrum, and they have strong Balmer breaks. Okay, so the first spectra of these objects, these universe-breaking objects, had really broad spectral lines, unexpectedly broad. This is still one of the best spectra of a little red dot. This is a little red dot taken to date. So you see the double break. Here's the first break. Here's the second break. But more importantly, what I'm pointing out here is that H beta, H alpha, these emission lines are kinematically broadened, which was reported in several papers at the time. One that coined the term little red dot for these because they are little red dots found by JWST. So why is kinematically broadened signatures, well, look at the headlines, a surprising ubiquity of AGN. What are AGN? AGN are active galactic nuclei. These are the cores, the supermassive black holes of galaxies that are accreting matter. So here's a primer on active galactic nuclei. The canonical model we have is that you have a supermassive black hole with an accretion disk of material around it that's heated quite a bit. Around that, you have ionized gas or in the broad line region, so a lot of hydrogen gas that's seen in recombination lines. And because it's whipping around so fast, you see it kinematically broaden. Beyond that, on parsec scales, you see maybe a dust torus of additional material beyond the dust sublimation radius. So this goes back to the AGN unification model in the mid-90s that was figured out. The point being that the broad line region, the width of the Balmer lines can be a direct tracer of how much mass you have within a certain radius. So that shoots through the roof when you have a black hole. Long story short, these broad lines are tracers of black holes. Okay, so the picture was gaining momentum that these are black holes, that these little red dots that were thought to be universe-breaking galaxies are not actually universe-breaking galaxies. We're looking at an accretion disk. But then that came into question because here's another paper that showed that little red dot spectra, or a stack of the spectra out into the mid-infrared was flat. Going back to that AGN model, you expect dust emission from the torus, at longer and longer wavelengths to rise and rise and rise. And that's just thermal emission from the torus. And we didn't see that. So the data are more consistent with this actually being a stellar population. It's flat. And it has a Balmer break, which we see in galaxies with older stellar populations. So that counters that picture of the torus emission. Also, supermassive black holes are readily seen in the X-rays when we look. This is from the accretion disk itself. They have these little red dots have no X-ray emission, which are otherwise pretty ubiquitous in the AGN population. And so nothing in the X-ray. And these are quite sensitive observations because all sensitive X-ray observations are in these deep fields already. So that was weird. We gathered, so still, the jury was out at this point about what they are. I think it still is at some level. But we had a lot of little red dots in the cosmos field, several hundred of these. So we could comment really well on the implication of their volume density, how common they are. Yeah?
How close they are.
Sorry?
How close they are. So the closest we see of them?
Oh, like to us?
Yeah.
Oh, that's the other weird thing is that they're really common in the distant universe, but virtually, we would have seen them with Hubble. We would have seen them with any other telescope if they were in the nearby universe.
This isn't clear why they stopped.
Yeah, exactly. Yeah, so they're ubiquitous. I mean, it's 5% of the galaxy population beyond a redshift of 4 or so. So they're everywhere in the first 2 gig years of cosmic time and absent after that. People have looked, found maybe 3, Yeah.
How much harder is it to observe the smaller black holes compared to supermassive black holes?
Oh yeah, so generally speaking, observed black holes that exist, there are stellar mass black holes, so it's the immediate remnants of high mass star that dies. We can see those locally, or we can see, they exist in the Milky Way. And then there are supermassive black holes that's in this regime of 1 million solar masses. And the picture by which you move from a stellar mass black hole to a supermassive black hole, that's a really unclear regime. We don't have direct observations of what are called intermediate mass black holes, the in-between. So that's a great question. I'll just shrug to that. Yeah, no, it's a big topic. People are dedicating their lives to trying to figure that out. So we see how common little red dots are. Here we're even cutting off the universe today, but little red dots are really, really common between redshift 4 and 9, and they extend previous measurements of the black hole accretion rate density. Sorry, I don't have a legible y-axis, but this is basically the number density of accreting black holes per unit volume in the universe. And the star formation rate density goes down, so the buildup of galaxies, it's low in the early universe, it builds low in the early universe and then builds up. But black holes seem to be steady, basically no change. Their volume density is unchanging, which might imply that black holes grow before the galaxies that they're inside of.
And that's assuming the black hole hypothesis, right?
That's assuming the black hole hypothesis. Yeah, that's totally right. Yeah, which, some people don't still today. But I would say, 80% of folks working on little red dots do. Yeah.
Is it possible that these black holes are hiding the galaxy around them?
Yeah.
Like the galaxy is already there, but we cannot see it because of observational constraints.
Well, yeah, so these images are super deep. Well, okay, this relates to that. Okay, so you take all little red dots, hundreds of them, stack them in the deepest data you got, okay? From literally the X-ray through the radio. So this is a really broad spectrum of little red dots. All JWST data is like right here, okay? You stack it, see what you got. It's a whole bunch of nothing. These are detected with JWST and not with anything else. So there's no X-ray emission. There's no mid-infrared power law that would trace a hot torus dust in a typical AGN. There's no submillimeter dust emission. You might expect submillimeter dust emission if these were not AGN, but like really compact star-forming systems that, star formation produces dust, and that would radiate as well, but we don't see that. And we have ALMA in that regime, which is a really powerful millimeter wave telescope. And there's no radiosynchrotron emission seen either, which is another kind of telltale sign of AGN. So this was pretty baffling. So this is from my grad student Hollis Aiken's paper, which the previous plot was as well. We tried to look for that submillimeter.
Can you just go back and explain what the line, like...
The red line is?
Yeah.
The red line is basically a made-up maximal SED, the maximal average SED for little red dots. Like, what could you accommodate physically that might make sense? Like what column density is required in the X-ray to produce a spectrum that is not detected in deep X-ray stacks. Here's the JWST stacked data, the average spectrum. And then what kind of dust SED could you assume at maximum and still fall under detection limits?
Okay.
Yeah, it's not really physically motivated. It's just like the max. Okay. So we went back in this dust regime because it turns out like the other very sensitive telescope that's in operation that can plausibly see these is ALMA, the Atacama Large Millimeter Array. So there's been a lot of effort to observe these with ALMA to try to find dust emission. That operates in the millimeter, rest frame 100 microns, but at high redshift. We push the depth an order of magnitude beyond what all archival data suggested. We still haven't found the dust in these systems. It nominally might suggest that dust is not responsible for making them red. Another key reason, I should back up. Another key reason why one might look for dust is because they are red. Red typically means dusty, astrophysically speaking, because dust reddens. So you can look for that dust in emission. We haven't found it. Okay, so an alternate explanation, which is really nice, that came online like late last year, earlier this year, or it's almost the end of 2025, seemingly. Yeah, so late 2024, middle of, or early 2025, is that you might not get reddening from dust. You might get a little red dot by virtue of a very dense gas cloud that enshrouds a supermassive accreting black hole. This is in this Naidu paper called a black hole star model. So it's effectively a stellar atmosphere surrounding an accreting black hole. This was so the theory behind this was published in this paper by Kohei and Nayoshi, and observationally there are some nice examples in Rohan Naidu's paper and Anna de Graaf, where there's a bomber break, again, that would trace a stellar population nominally, but it's a really, really strong bomber break, so much so that you would not see such a strong break from a stellar population. You cannot reproduce this with a normal stellar population. Here's the other one. This little red dot is called the cliff because of the cliff drop off in emission right at the bomber break. And you can quantify the magnitude of this bomber break, and these sources are too extreme for aggregate stellar population. So we don't think the emission is from stellar origins. Yeah?
Then why would the black hole star would make that big break? Is because it has a short life, or
No, so the break in this case is saying that it has a single solitary, very dense gas envelope causing absorption. So the gas is collisionally excited to n equals 2 and then causes this extreme Balmer absorption of the continuum blueward. So intrinsically the AGN accretion disk would keep rising, but this dense gas envelope absorbed it. Yeah.
So do they in the Naidu paper, do they also address why we don't have any X-ray emission?
Yeah, I don't recall offhand. I'm not on. I don't know. I wasn't involved in the work, but yeah, probably.
I mean, you're not seeing the disk in that.
Yeah,
scenario,
yeah.
Right.
Yeah, yeah, yeah.
So you can't.
Yeah, I
too
mean,
much
you're
column.
basically not seeing everything. You're
Okay.
totally behind this thick atmosphere. So yeah, I don't know if they actually wrote a section on that or not. It's a Nature paper, so you can't fit much in it. So, another interesting interpretation of this is along the same lines that you still have dense gas, but you might not have this contrived situation where you have a spherical distribution of a stellar atmosphere around a black hole. This is this paper by Hanfu Liu, who's a grad student, I believe, at Princeton. You know, you could explain this through super Eddington accretion, and the fact that you might have just a really dense gas envelope but distributed in a disk. So what is super Eddington accretion? At a very low level, just quick explanation of that. You have an accreting black hole with an accretion disk. I mean, anything can, you have this balance of forces, of course. You have gravity, and then you have radiation pressure from the light of the accretion disk, pouring out. And the idea of super Eddington accretion is that the radiation pressure is so high that it can basically blow out it exceeds the pull of gravity, and so it's an unstable situation because there's so much radiation pouring out of the system.
How does it explain the lack of X-ray?
How does it explain the lack of X-ray? It's a good question. I'm not an X-ray. yeah. I can go look it up. Yeah, that's a good question. So this can produce a Balmer break if you have something like 5,000 Kelvin photospheres at a certain density and super Eddington accretion. Then if you have super Eddington accretion, this is not thought to be long-term stable, of course, because you're blowing it out. But perhaps that is telling us something interesting about the life cycle of these things, or they are quasi stable or something. One other last question before I end, I'm out of time here, is where the host galaxy is. So if these are supermassive black holes, little red dots are supermassive black holes that are accreting one way or another and may or may not have this gas envelope, we still haven't seen the host galaxy, the stellar population around these systems. This is the ratio. Here I'm showing a plot of black hole mass versus black hole mass to stellar mass ratio versus stellar mass, going all the way up to 10 to the 11. The local relation, there's kind of a nominal local relationship that you expect a black hole mass to be roughly 1,000th the mass of the stellar population of a galaxy. But that's definitely not the case in these little red dots. Any constraints that do exist in the territory of high redshift AGN found by JWST imply much more equal ratios. So the black holes are really massive. Here I'm just showing you the 1-to-1 where the black hole would effectively be as massive as the galaxy containing it, which is pretty bonkers. So it's a mystery where the host galaxy is. Many are starting to think that the host galaxy of little red dots exists, like we can see it in the rest frame ultraviolet. That basically the red portion is the black hole here, and that these have these funny spectral shapes because they're two different components. There is quite a lot of variety in the rest frame ultraviolet signatures of little red dots, possibly indicating that the diversity of host galaxies or the stellar population surrounding these systems. Here's a little cartoon of what that might look like, where in one scenario, a lot of these data don't exist yet. These are made up data. Okay, we want to gain more spectra of these sources to infer. But if you were to see a host galaxy, you might expect different spectral signatures than if we're looking at emission from the black hole itself in the rest frame UV. So we hope to get these data and understand more about what they might tell us about the host galaxy. My graduate student, Hollis Akins, has a medium-sized program in Cycle 4 to do just this. It's called the EMBER program, where we're getting spectra of a very large number of little red dots to understand the true underlying diversity of the population and hopefully learn more about the sources contained. Okay, I'll end there. Here I have the summary. I have a very simple summary for a broad audience that JWST has found an unexpectedly bright and early galaxy population, something like 10 times more numerous than predictions, and we're trying to figure out if early star formation is super efficient. And then little red dots, I would say the best thing of a consensus view of what they are right now is that little red dots are supermassive black holes in formation. They accrete efficiently, they might be super Eddington, and they're surrounded by dense gas. And we have yet to really learn more about their host galaxies. Thank you for your attention.
I have just a new question about super Eddington accretion. Like physically, how should I think of it? Like, is stuff somehow being pushed in faster than I expect, or is there some non-symmetric accretion going on, or how should I?
Oh, that's a good question. I mean, again, this is out of my wheelhouse a little bit because I just observe these things, so I don't work on the models. But if you put, Eddington limited luminosity or super Eddington. It's a broader phenomenon than just speaking about the exact model of accretion onto a black hole. It's basically, are you producing enough radiation to exceed, the gravitational force? So that can happen in broad context. But in the accretion disk, I think there are lots of different models of how you get, very dense gas localized, within a parsec of this supermassive black hole, and these models are, highly complex, right? But there are many different avenues to deposit that gas. You expect, you almost expect some. You don't expect these black holes to form in isolation, right? So they're embedded in some surrounding they must be embedded in some surrounding stellar population and the dense gas cloud that led to that in the first place.
Obviously you're an astrophysicist, not a cosmologist.
That's right.
I was wondering, are there cosmologists that look for a more like a cosmological solution?
Yeah.
Amendments to lambda c, and like what is the general thought process behind whether this is an astrophysical or cosmological?
Yeah, my philosophy on this is it is astrophysical unless we can prove that it's not astrophysical, because that's the simplest explanation. I'm not going to go change cosmology.
Yeah.
When astrophysics itself is so messy.
Despite what New York Times wants.
Yes! But I'm okay with the headline. It's all right. It's better than some other New York Times headlines. So there are cosmological explanations. For example, if you evolve early dark energy, or the early dark energy model, if you inject more or an evolution of W, then you can allow for the that would fix the formation of more massive halos earlier on in cosmic time, and also consequently fix Hubble tension. So that is, you all, I'm sure, know much more than I do about it. But the cosmologists at least.
I missed what was the cost of just interpreting the little red dots as without the supermassive black holes, just as really bright
Is
galaxies?
that really? Yeah.
What was the cost?
Well, so it's just more. So they can be interpreted as galaxies. Galaxies, really, I mean, very dense products of giant molecular clouds that formed very efficiently. The stellar mass density of them is very high. It's equivalent to the cores of local elliptical galaxies. These are the densest regions that exist. They don't exceed that by orders of magnitude. There are some examples that do exceed it, kind of the maximal stellar mass density. But, that's allowable. I would say probably the biggest issue with the interpretation of them as galaxies is the kind of contrived geometry you would have to use to explain this type of spectral shape, and the spectral shape is somewhat ubiquitous. That you have a red optical continuum, and this would be attributable to an aged stellar population, but then you have this recurrent UV emission that is quite blue. So you would have to have superimposed a really recent but lower mass, but a very, disproportionately lower mass burst of star formation after the formation of a much larger stellar mass reservoir. So it's just contrived.
I think I got just two quick questions on the little red dots.
Yeah.
The first is, do you need the black hole star and Super Eddington together, or can you just explain it using one model or the other?
You can explain it one model or the other.
Okay.
There are issues with both, I think, that aren't figured out entirely. There are you have to hand pick the temperature of the photosphere. You have to kind of or how do you get this spherical distribution of gas around your black hole rather than, the typical disk structure. So both scenarios are not perfect.
Yeah, so my second question is on the black hole star scenario.
Yeah.
Do we have a rough idea of the scale of it? And then, how is it spherical? Is it spinning, turbulent? Might we expect some
these are very
sidelines?
sophisticated questions. No, I mean, basically, the whole premise that you can produce this with really dense gas, those are all gathered from 1D simulations that if you just put a slab of gas in front of a black hole, and it's assumed to be spherical because it's also a ubiquitous feature of these sources that are probably oriented in random angles. So yeah, it's not that sophisticated, I would say. Yeah.
Thanks for the great talk. Maybe you said this and I just missed it, but when you were showing the black hole to stellar mass ratios towards the end.
Yeah.
Are the black hole mass estimates there folding in this picture of Super Eddington or black hole star, or is it sort of a traditional?
Traditional.
Okay. It's
traditional. So it's through the Balmer line widths.
Right.
Dynamics. Yeah.
Okay.
Dynamical estimates of the black hole. I will point out that these, I don't love these measurements because, little red dots, I told you we don't see the host galaxy, but people, nevertheless, it doesn't stop them from guessing the halo mass, or the host galaxy mass. These aren't all little red dots, so there are some scenarios where you do see a host galaxy, but and with a black hole. It's not perfect. Yeah, these measurements aren't great. But something's up.
We can all agree. All right. Let's thank Caitlin Casey for